Here we go. I'm sharing my screen. It's recording. That's great. All right. The final exam schedule is posted, and our final exam is nice and sort of early. December 13th from 1 to 4, which is a very nice time slot in E208. Now I should go back and see, because I can't see the chat, which is making it kind of difficult when you guys are all just online. Hello, I'm here. I wanted to ask you guys if you would prefer to not have a new lab and just wrap up the old lab. Oh yeah, and the last question on the quiz, I just marked it before my last class. So you should have your adjusted grades now. Nice. And there should be a little bit of feedback if I had any. Nice. So let's tackle that first. Oh, I've got these little cuties. Whee! Great job on test number 1. You guys are quite the memorizers. I thought it was going to be so hard and so long, but you did it, and I'm so happy. All right. Yeah, I wish I had a laptop or something so I can see the chat, but that's okay. So you did great. What else was it? Oh yeah, I was gonna ask if you guys wanted to have a new lab, because I was looking at kind of the schedule that I posted before, but I didn't really know if it was gonna work or not. But we were supposed to do lab 5. Let me just screenshot this. Bring it in. Wonder if there's a way to have the chat open. Oh, wait, maybe not. Okay, that's okay. Oh, there. So if I go in here, we were supposed to have, and I don't know, I think I just wanted to, I'm trying to remember what my thinking was. I think I wanted to spend a lot of time in simple linear regression, just to review from Stat 230, because I know we went through it and it was crazy rushed. But I think it makes more sense to just follow the textbook. So I was going to do just a simple linear regression lab, and I still can. But the other option is, if we don't have a new lab this week, then you can just work on lab 4. So I'm curious to know what you would prefer. If you want a new lab or just work on lab 4. Work on lab 4. You got it. Okay, the results are in. So I'll put it in my notes, make it official here. We'll cross this off. No new lab. Work on lab 4. Okay. Which of course is this one. Okay. Because I am going to go a little bit past simple linear regression, but not too much yet. Yeah. Good. Gets confusing with these two boxes. Uh, oh, is the you don't like the lab, huh? Uh, that's okay. I don't like the lab either. Because we should just be doing it in class. Is the deadline extended? Now that's a good question. Yeah, how about I extend it till I want you guys to have worked on it. Right now it's due tomorrow night at midnight, but I guess I could extend it till next Friday. Seems like a lot. Why not? Extended until next Friday. It's kind of a tricky one, this lab, right? But what it's doing is it's just getting you to rework the code from the textbook to answer the questions. Okay. All right. So let's scoot that to the side. Oh, maybe I can do something cool like, how do I, like this. Yeah, so lab 4 was the one with the extension. So now I have the chat so I can see it. I might forget to check it, but let's that's something. Um, mm, oh, is it giving you grief with the decimals? Uh, what if you, yeah, so if you send me whichever one and then I'll run it on my end, see what I get, and then I'll adjust it. Okay. So whichever question it is that's giving you grief, I don't have a pointer in Zoom, but I do have a pointer here. So if some of the questions are acting weird, then let me know and I'll have a look. All right. Okay. So totally fine. Okay. What are we starting today? So today we're starting chapter 4. Chapter 4 is regression and chapter 5 is going to be classification. The only difference really is whether the outcome that you're trying to predict is numerical or categorical. So in chapter 4 it's numerical, so you're predicting numerical outcomes, and in chapter 5 you're predicting categorical outcomes. Okay. But we kind of lump them together. Oh. So chapter 4, it's tricky because it's, can I, no. All right, can't win them all. Is on regression and prediction. Oops. Now, regression and prediction is, so regression specifically is for predicting numerical outcomes. All right, so numerical outcomes. And then chapter 5 is on classification, where we basically do the same thing, but we're predicting categorical outcomes. it's going to be important that you keep this distinction in mind, right? Because right now we're going to start and we're going to talk about predicting numerical outcomes or modeling numerical outcomes, but then we're going to move towards categorical outcomes in chapter 5, right? And establish those techniques. So we'll be able to do both. And I would argue to be a good kind of a solid data scientist in terms of statistics, these are the two main things that you need to be able to do really well. Okay. So let's take it back a notch. And for regression, right, we know from Stat 230 that we use a straight line to model a relationship if we have a linear relationship. So what we've seen in the past looked something like y hat is b0 hat plus b1 hat times x1. Okay. Just a reminder on what these things are. Y hat is the predicted value, and maybe I should use a different color here. Spice it up. Y hat is the predicted value of y. Nice, same color. B naught hat is the intercept, the y-intercept, but usually we just call it the intercept. And then whatever's attached to the x, in this case x1, is going to be the slope. Notice how we only have x1. Of course, later we're going to build up to x1, x2, x3, right? And so this is one predictor variable, predictor or explanatory variable. We'll try to, or I will try to call them predictor variables as often as I can. Okay, but when we have one predictor variable, that's what makes it simple linear regression. Whereas if we have more predictor variables, then we have multiple linear regression. So this one predictor means that's what makes it simple linear regression. Okay. So y hat is the predicted value of y. And so what we're trying to find is we're trying to use these estimates of the slope and the intercept with some value of the predictor in order to predict the value of y, the outcome. Okay. Let's jot that down. So we use regression to predict outcomes. These with the hats, so B naught hat and B1 hat, those are the estimates for the slope and the intercept, right? But of course, there is some true relationship, so some population relationship. So there is a population intercept and a population slope that we're trying to estimate using these, using the sample information. So we crazy. We use sample information to build a model, of the population relationship. Which looks like what? Looks like y equals b naught plus b1 x1 plus the error term. So I guess they've used e, I should match the textbook. make it nicer, plus some error term. Okay. This captures the entire population relationship, but this is our estimate, right? So we've got a slope estimate and an intercept estimate. Okay. So now, right, this is what we're trying to model. What if I have more than one predictor, right? So all of a sudden we're done with simple linear regression, which is this, right? Where I just have the one predictor. Just a second. Someone's finally here. Whoops, sorry. Quite all right. Everyone's online. Oh. I know. So you're, huh? I know it now. Like, okay. I guess I should display it. It's fine. Let me just get set up here. Hold up, hold up. Let you get organized too. We're just reviewing some regression. Simple linear regression at that. We did decide no new lab this week, just work on lab 4, and I'll extend the due date to next Friday. But there are, I guess, some values that aren't working. So if you do find that, then just send me an email and I'll check it and make sure that what you're doing is actually right. And then it probably is, and then I'll fix it. How about that? Oh, this isn't even on. Did it? Oh, didn't do it. All right. Just so you don't think I'm crazy, there are people online. I'm not just talking to myself. And I feel like there was one more, but I can't remember. I can't remember who it was.
We're doing linear regression and machine learning as well.
A lot of overlap. Nice. Okay. Now I won't be able to see the chat anymore because now when I'm displaying, I am going to. I closed the window, but I wasn't thinking. Question is, am I still? I am still recording. That's crazy. All right. Sorry about that. Finally set up. Quite all right. But this might look familiar, right? So we're trying to model this relationship here. And what I was building up towards was, well, what does it look like if we just have more than one predictor? Well, we can go for as many predictors as we want. So what if we have more than one predictor? X1, X2, X3, etc. that I want to incorporate into my model. That seems perfectly reasonable. Right. Now that it's not just me in here, I'll make sure you can see the screen.
Oh, I think all of us in person.
There. Okay. So what if we have more than one predictor that we want to incorporate into the model? Oops. Into the model. Well, I can just add them. B0 plus B1 x1 plus B2 x2 plus all the way up to BP xp, right, for some number of predictors plus the error term. There. And so here, what I'm allowing for, right, x1, x2, all the way up to xp, I'm allowing for p predictors or features. Allowing for p predictors slash features. Okay. Now, what I used to find kind of confusing is that this is no longer a straight line, right? But it is a linear relationship because we're adding all these features in, right? So because I'm going some coefficient times x1 plus some coefficient times x2, right? They're all being added in linearly. So we still call it a multiple linear regression, but it's just the multiple is the more than one x, and the linear is them being added together. Okay. This is a linear model because the predictors are added because, and maybe that's enough, because the predictors are added. Okay. So let me just clarify, because I know I was, and maybe you guys are smarter than me, but I was super confused about it when I was learning about it. Multiple linear regression, just the terminology threw me off for some reason. Now I'm not really sure why, but I remember it being an issue, so that's why I want to point it out. Is when we have more than one predictor. Added to the model. How we fit this multiple linear regression is the same as what we did for simple linear regression, right? How we find B0 hat and B1 hat is through by minimizing the residual sum of squares. Right? And that's just the method that we use. There are other methods, but this one, especially when it was kind of computationally expensive, it was the cheapest way to do it. But it works quite well, so we still do it. But we fit a model, or we fit the model by minimizing the residual sum of squares. That's the same as for simple linear regression. So we still use that same method, which means what? It means that we're gonna have residuals still, right? And so we're gonna just minimize those residual distances, the sum of the squared of the residuals. Yeah. And I guess I wasn't done here. And we find that y hat is b naught hat plus b1 hat x1 plus, let's do b2 hat x2 plus all the way up to bp hat xp. There's no error term anymore just because we're estimating now. Okay, and so these are estimates for the coefficients. Okay. And these are the values that we get with our output. If we ask for it, right? If we fit a linear model, it'll give us these estimates for the coefficients. And I do have it pulled up, and maybe I should wake it up so it doesn't fall asleep on me here. I do have the code for chapter 4, and I might just kind of run through some, but yeah. So I might run, oh, I knew it would go to sleep. Okay, fine. I'll let it sleep for a little bit. I was hoping I could get back in there and wake it up, but that's okay. All right. So these are the estimates, right? And we get these from the linear model output. We get these estimates from the LM, that looks like lawn. From the LM y tilde x or x1 plus x2, x3, blah, blah, blah. Output. Which if I don't get to it, we'll definitely look at next week, especially in the lab. All right, so one of the things that we need to decide to do or kind of deal with is if we have missing data, right? So what are some of the things that we can do? And there are very sophisticated things, but one luxury of having a large data set is that we can just remove missing values, right? And so that's going to be what I would recommend most of the time, is just remove missing values, assuming you have a large enough sample. Right. So if you have a large enough sample and removing, you know, however many missing points isn't going to hurt you, then just do it. Yeah. I'll put it on a fresh page here. So as we fit the model, we need to decide as we fit the model. We need to decide what to do with missing data. Okay. There are kind of fancy ways to deal with it, right? But like I said, one of the luxuries that we're probably going to have is that we're going to have large data sets. So since we will often have large data sets, oops. We will omit, which means remove. I use the term omit because it's part of the code, remove or delete missing data for simplicity. Okay. In the code, in LM y tilde x, let's do x1 plus x2 plus x3. You're gonna do NA dot action equals NA omit. So you just tell it to omit all those values. And that's going to be the easiest way to deal with it, right? But if you find that it's deleting most of your data, then you have to find a more clever solution, right? Yeah, so you can do imputation things, which is kind of most common. What's another way that you could deal with it? You could use linear regression to impute values. Seems weird, but you can. So here, let's just follow it up with missing data. Because it's good to be aware that there are kind of fancier ways to deal with this stuff. But
sorry, Emily, sorry to
us-
cut you short.
oh,
Yeah,
oh.
the screen is off. Sorry.
Oh, sorry. I don't know. What, has it been off for a long time?
For like say a few minutes now.
Oh, I'm so sorry. And I'm sure it was, oh, you said it in the chat and I didn't see it. I'm so sorry. Because I can't see the chat. Thank you. And also kind of fun, it was, your voice was broadcast in the room over the speakers. So you can take advantage of that. Hopefully it's showing now. Sorry about that.
No, it's not. No, it's not.
It's not showing.
No.
Okay. It
You
just
have to
said a
come to
little.
class next time.
I know I don't have my online lecture set up here. I don't know what I'm doing. Let's see here. It says I'm sharing, but you can't see it, huh?
No.
What if I stop? I'll stop sharing and then I share again.
Okay.
Start, 3, 2, 1. How about now?
Still not showing.
Still not showing.
Just go on listening.
But you can't see anything.
Yes,
I'll
I can
have to
see.
dictate.
Yes, I can see. Yeah.
Can you
Thank
see
you.
now?
Thank you. Yes.
Okay.
Yes.
And where do I need to scroll to?
Yes, that's fine.
Okay. There.
Thank you.
Usually I have like another screen so then I can see what you're seeing. So then and see the chat. I don't have anything like that set up here. All right. I'll let you guys get caught up. I wonder if I can keep writing here. This part, I think you guys know, but there are many different ways. And is it Bevan who's doing machine learning? Yeah. Does he make you do any imputation stuff? He does. Good. Of course he does.
So sometimes he's like, you should impute with a 3-day rolling average.
Mm-hmm.
So
Oh yeah, financial data, they do love that rolling average. It makes sense, I guess. But you can, yeah, you can do all kinds of weird stuff. In fact, there are many different techniques. I guess for financial data, you would need to have, yeah, you can't really do it with missing values. Like you couldn't really remove months worth of data, right? Especially for time series, it would be really important. But for us, let's just remember that there are many different techniques for dealing with missing data. Of kind of varying levels of sophistication. Just taking the average and imputing the average is one of the options that's not very sophisticated. The rolling average would be kind of a little bit more sophisticated. You could do kind of a linear model imputing. And the problem is if your data set is small, then you'll need to deal with your missing values. You can't just delete them all. You'll be left with nothing. And if your data set is small, you will need to deal with your missing values. I guess instead of just removing them. I used to talk to kind of the biology grad students. They had their office next to ours. And so some of them would be like, oh yeah, but I just removed those points. It's, oh no, those were outliers. I just removed them. What? You did what?
My friend is in biology. She says I want to learn statistics.
I know, yeah, because all they want to do is just remove all the nasty things. It's like, well, that's where the information is though. So don't do that. But yeah, it's so funny. Okay, so that's missing data. So once we have run this model, for example, it's really important that we need to be able to interpret these coefficients, right? What's the output that we're getting here? So once we have run the model, we need to interpret the coefficients. You might remember from Stat 230, right? In simple linear regression, the interpretation is pretty clear. In simple linear regression, that's when we have y hat is b0 hat plus b1 hat x1. Let's specify. B0 hat is the y-intercept. What's the definition of the y-intercept? Well, the y-intercept, remember, is the predicted value of y when x is 0. The predicted value of y at when x, I guess in this case, or x1 is 0. B1 hat for a simple linear regression, right, is going to be for each unit increase in X1, I expect to see a beta or B1 hat, it is beta, but B1 hat increase in the predicted value of Y. So the slope for each unit increase in X, or in this case, X1, we expect to see a slope increase in the predicted value of Y. In the predicted value of Y. Okay. When we extend this to multiple linear regression, we have to change, well, the intercepts is the same right now. All these values of X are 0, right? But for each of the coefficients, right, we have to add this this layer of assuming that everything else is held constant. Okay? So we can only interpret one coefficient at a time. So in multiple linear regression, we get Y hat is B naught hat plus B1 hat X1 plus B2 hat X2 plus, oh, let's allow for BP hat XP. So again, the interpretation of the intercept stays the same. It's the predicted value of Y when all the X's are 0. When all X subscript I's are 0. And in general, let's talk about some BI hats. Okay. Because we do interpret them all in the same way, but it's going to be, and it is the same-ish, okay, for each unit increase in whatever X it's attached to, right? Then we expect to see a slope increase in the predicted value of Y, or a coefficient increase in this case, assuming that all other things are held constant. Okay. So what we're going to say here is the predicted value of Y changes by the coefficient BI hat for each unit change in XI assuming all other variables remain the same. Assuming all the other variables XK, and I'll clarify here for K not equal to I, of course, remain the same. Okay. Maybe I didn't need to keep this RStudio Cloud. I just realized, let's see here. I think the multiple linear regression example, which is kind of what I'm more keen on using, uses a different data set I didn't bring in yet. Easily fixed, but did you guys see RStudio Cloud is becoming Posit? They're renaming it, rebranding. I was reading, I guess they figured RStudio Cloud was too specific when they actually can do other programming languages than just R. So it was kind of restricting them a little bit. Let me see here. Multiple linear regression using the sale prices, and I brought in the lung data. Come on, that's okay. I'll save it for next week. For now, I guess we can keep talking about, okay, so if I've built this model kind of so far just in theory, right? But I need to be able to figure out if this is a good model or a bad model. I guess black and white. All right, so once I have built the model, I need to be able to determine if it's a good model. To be able to determine if it is a good model. I'll put good in quotes. What does it mean to be a good model? Walk the catwalk. No. It means that our predictions are close to the actual outcomes, right? A good model means that our predicted values predictions are close to actual values of Y. Or rather, maybe I should say predictions, which are really Y hat. Y hats are close to Ys. So let's talk about some of the tools that we have, and there are a lot of tools that we could use. Everyone's competing for the best tool. Usually we use a combination of tools just to kind of say, okay, well, judging by the root mean squared error, for example, if I compare that to the AIC, I have a good model because both of these are giving me good results. But let's talk about them first. So assessing the model. I'll preface it by saying that there are lots of different metrics that we could use. Okay. I'm just going to outline the most common ones. And honestly, just using these is plenty. There are many metrics we could use to assess a model. The first one is the root mean squared error, which you've probably heard of once or twice. I know we talk about it in Data Science 300, but we don't really kind of talk about what it is, or at least I don't think so. But it's the root mean squared error. And how we're going to find it is by a square root, and it's the sum from I equals 1 to n of yi minus yi hat squared over n. Notice that a good model is the distance, so the predictions are close to the actual values of y. And here we have yi minus yi hat. How far are these observed values of y from the predicted value of y? Right, and so this, I think I cut you off, but it's the residual. Which I feel like you were going to say, or probably did say, but I was too excited. All right, so this is the residual. And so then I square the residuals and I add them all up and I divide by n, and then I take the square root. Hence the root mean squared error, right? Root mean squared error. Whew. It's all in there. All right, so the residual or the error of our prediction. Okay. What does that mean? Do I want to maximize or minimize this thing? Because there are going to be scenarios where we're going to want to maximize, but in this case, right, we want to minimize it because I want to minimize this distance, which means I want to minimize the square distance, which means I want to minimize the sum and the mean and the square root. Okay. What color can I use here? Green, maybe. We want to minimize the RMSE. Yeah. So our job, we have to keep track of what we want, right? If I'm comparing two models, right now I would choose the one with the smallest root mean squared error. Okay. The default output in R gives you a slight variation on the root mean squared error. I'll put on a fresh page here. The default output in R gives the residual standard error. RSE instead of the root mean squared error. So even though it's kind of the most common and we can find it, we can ask for it, right? But in terms of the default output, it's not there. And the reason for that is because the root squared or the residual standard error, I always want to use the same words. They're not. Looks the same. Okay, so what does it look like? The root squared, the residual standard error. I keep messing it up. It's because they're so similar that I just assume they're going to be the same words, but they're not. Is the sum from I equals 1 to n of yi minus yi hat squared. So far, this looks the exact same, right? Divided by not just n, but n minus p minus 1. So this is the only difference, right? I'm subtracting p, which is the number of predictors. So here, RSE penalizes models with many predictors. Of course, you're going to get a good model if you're incorporating all these predictors, right? Of course, it's going to do a good job. The more information that you give it. However, when you take that model and you apply it to a new data set with the same variables, you're probably going to lose a lot of that good modelness. If that makes sense, right? And so, so that's why it penalizes you for having too many predictors in there. You've overfit the model. So RSE penalizes models with many predictors. Oh, someone trying to reach me on here or what? Screen sharing. Ah, sorry guys. Okay. I don't know why it's cutting out. I wish I could see it. Everyone else left. Now you can see it. Okay, nice. Good. Okay, sorry. I don't know why that's happening. Maybe what we'll do is I'll just finish talking about this. Okay. With many predictors. Where P is, of course, the number of predictors. This n minus p minus 1 is the degrees of freedom. Not that that's important for us, but one thing to keep in mind, right? If my degrees of freedom is n minus p minus 1, that means that my n always has to be larger than the number of predictors in my model, right? Otherwise, I run out of degrees of freedom. Okay. So here, we need to have n larger than p so that we still have some degrees of freedom, or so we don't run out. Oops. Don't run out of degrees of freedom. Right. It also is going towards over predicting the model. Right. Okay. What's interesting is that for large data sets, so when n is large, right, assuming I don't have a crazy amount of predictors in there, right, this n minus p minus 1 is not going to be that different from just n, right? If it's huge in comparison, then the root mean squared error and the residual standard error are going to be very similar. And so for large data sets, right, so n is large. The root mean squared error will be similar to the residual standard error. Okay. I did, right? Like, I blanked out. What did I say? I have to really think about it. Okay. I think what we should do is, because my Zoom is acting up, are you okay if we pick it up next day? Okay. Which I guess isn't until Tuesday. Are you okay with that? I think only Darnpreet's here. Oh, nice. Yeah, because this, okay, awesome. This Zoom business, I don't know why it keeps glitching out. Anyways, thanks for coming. And I'll stop this recording.